Thank you for everyone for joining us today and welcome to our C2M2 Distinguished Speaker Series. I would like to introduce Dr. Master Ronnie Chaudhry to go ahead and introduce our speaker for today.
Thank you, Charlotte. This is Ronnie Chaudhry. I'm the Director for Center for Connected Multimodal Mobility, C2M2. We are glad to have Dr. Angshuman Guin among us today. He's our distinguished speaker today. Dr. Angshuman Guin is a senior research engineer in the School of Civil and Environmental Engineering at the Georgia Institute of Technology. He returned to his alma mater to become a faculty member in 2007 after working in the industry for a brief period. Dr. Guin's current research at Georgia Tech are broadly conducted in the area of freeway operations, connected and autonomous vehicles, intelligent transportation systems, transportation safety, traffic simulation, and data management. Dr. Guin has presented his work at several international conferences, and his work has been published in well-recognized peer-reviewed journals. He serves on several standing committees of the Transportation Research Board, including the committees on information systems and technology and human factors of infrastructure design and operations. In addition to maintaining an active research portfolio, Dr. Guin is a strong advocate of translating research into practice and is the co-founder of a data analytics company. It's my pleasure to welcome Dr. Guin.
Thank you, Ronnie, for the kind words. So I'll jump right into this. So let's talk a little bit about machine learning. So with the current explosion of data and computer power and or computation power and advances made in the area of natural language processing, voice recognition, and so on, we hear the words machine learning, deep learning, artificial intelligence bounced around a lot. And whether we notice it or not, we are enjoying the benefits of machine learning in our daily life when we are asking Alexa or Siri or Google to set an alarm, or when we are sorting through the recommended videos in YouTube, Netflix, or Amazon Prime, right? So the question naturally arises in our mind: how powerful is this thing? Should I be using it in my research? So today, I will not go into the depth of what machine learning is or deep mathematical formulas here, but I'd like to present to you a few examples of how we at Georgia Tech in our ITS lab, we are using machine learning in traffic operations research, and hope to demonstrate some potential uses and get you your creative juices flowing. Well, so just so we are talking about the same thing for today's discussion, that the definition of machine learning is that it is the use and development of computer systems that are able to learn and adapt without following explicit instructions by using algorithms and statistical models to analyze and draw inference from patterns in data. It's not magic. You essentially allow the machine learning model to learn from a training data set and use it to produce your desired output from actual data input. So machine learning approaches are traditionally categorized in these three primary categories based on the type of feedback: unsupervised, supervised, and reinforcement learning. Although those are getting blurry, even so it's questionable how you put one of the methods in one category. So, but broadly, in supervised, you label the training data to say which output is correct and which output is wrong. In supervised, you do not provide any such labeling, but rather rely on the natural partitioning in the data set to gain insights on the data behavior, or just mine for information. In reinforcement learning, you do not provide explicit labels, but rather reward the model when it gets the answer correct. So, however, the recent learning models do not necessarily fall strictly into one of these traditional categories. Deep learning is one of these learning models that has become very popular in recent times. So I have some examples of each of these once we'll look at some unsupervised learning. And there's one with deep learning, and then there's one which is currently under progress. So we don't know what the exact procedure there will be. Okay, so with those basics under our belt, let's finally dive in. The first project I have here is a Georgia DoD project that studied the feasibility of advanced or alternate traffic incident detection technologies. In the first part of this study, we looked at the feasibility of using crowdsourced information for incident detection. In this part of the study, we did not use any machine learning, but putting this here anyway, just to provide context for the next piece of the study that actually does. And personally, I think that looking at the WAZE data is interesting. Anyway, so in Atlanta, like in any large US metro, we have an extensive incident management program. The effectiveness of the program is, of course, directly related to the successful and timely detection of the traffic incidents. At the core of the operations is Georgia DOT's Transportation Management Center with its army of floor operations and supervisors who are the eyes and ears of the incident management program. By monitoring the 511 calls and monitoring the cameras along the freeways that are spaced out about 1 mile apart, they're able to detect the incidents within minutes of the incident occurring and dispatch help. So Georgia DOT has a partnership with WAZE, via which they can access WAZE's data. So for the crowdsourced data for this project, we chose the WAZE data set that was available through Georgia DOT's agreement with WAZE. And we started the feasibility study with a straight up comparison of the WAZE incident logs with the Georgia DOT's incident management logs. So Georgia DOT's advanced transportation management system is called Navigator. So I might slip into calling them Navigator logs, which essentially refers to the same thing, GDOT's incident management logs. It's the performance measures for the evaluation would be the time to detect and the detection rate. That is whether WAZE is finding the incidents faster than Navigator and if WAZE is getting all the incidents. So for this, we took the WAZE logs and the Navigator logs and performed a data fusion. So given the amount of details available in a WAZE incident description is very limited. I don't know if you have seen any of those, but it's because it's based on people clicking and choosing options when there is not any much room for detailed description of the incident. So there wasn't really a way for us to establish a one-to-one match with 100% certainty. And we had to resort to a method of filtering across multiple dimensions that would lead us to the incidents in the two logs that we can claim to be referring to the same incident with a high degree of certainty, not exactly 100%. So we looked at the time, address, the direction, and the distance. So from an algorithmic efficiency standpoint, the first thing to do was work with the number instead of the text. So we looked at the timestamps. So unless the occurrence timeline, that is the time between the start and finish of the incident, unless that overlapped by at least 25%, we rejected the possibility of the logs referring to the same actual incident. It is somewhat a little aggressive. Means we could go with a lower percentage like 5% or 10%, but we stuck with 20% to ensure that we can have a high confidence in the match. So next, if they did have an overlap, we checked for matches of the number in the primary road. For example, for in I-85, the number would be 85. We look for if 85 was found in both the logs. Then we looked for the full name of the road. And finally, we looked at the name and number in the crossroad. So if any of these are found, then in both the logs, then we move on to the next step where we look at the direction If the direction matches, then we look at the distance. So essentially, we're doing a search in the space-time map, right? Um, the results of this matching process, when we plot it on the map, it looks somewhat like this. In the top set of these maps, the blue points indicate the navigator incidents, and the red points indicate the WAZE points. So these are points over a 3-month period, flattened out. So the time scale is orthogonal to the plane here. So it's essentially we have a lot of overlapping points. The bottom set of maps show the matched points. So when we look at it here, it looks absolutely fantastic until, of course, we look at the raw numbers. So, but these numbers are not too bad either. We have about 42% of the incidents that matched. 42% of the incidents in Navigator, in the Navigator logs that matched with WAZE. And since WAZE had a much large number of incidents, we had 78,000 incidents in the WAZE log, we had only 3% of those matched to the Navigator. Okay, so we had 2,400 matches, so that represented half, almost half, a little less than half for Navigator, whereas it's only 3% for WAZE. Anyway, so this 3% number was not a big surprise, because we know that there are a lot of minor events, like somebody pulling off on the shoulder, that gets tagged as an incident WAZE, but are usually ignored by Navigator because they clear by themselves and do not need an intervention. However, the unexpected observation was that not all of the Navigator incidents were found in the WAZE logs. So while we don't have a surefire way to explain this, we do have a couple of hypotheses. Likely one is possibly that the location of the incident was off in one of the logs, or maybe the timeline of one of the logs was terminated prematurely, which prevented a 25% overlap. But more importantly, we cannot eliminate the obvious one, that there was nobody running WAZE driving through the area at that time. Or if there was, the WAZE user did not care to log the incident. So these are quite possible during low flow conditions. Right? So this does question the reliability of using WAZE as a complete alternative to other detection methods. So I'll skip through this. Next, we compared the time to detect the incidents in each of the methods. So the plotted distribution, we plotted the distribution of the difference in the detection times. A positive detection here means that the Navigator detected the incident first, while the negative detection on this side of the dot of 0 indicates that the incident occurred in the WAZE log first. The split was close to 57-43, which means that the majority of the incidents were found earlier by WAZE, but it was not quite close to 90% as we would have liked to believe. The behavior was steady across the different months, February, March, April, and this is the aggregate across all the months. So we sliced the data on several different dimensions to see if there were specific conditions under which WAZE provided significantly better or worse performance. For example, our hypothesis was that if there were low volume conditions, then maybe WAZE is not good detecting all the incidents. So there will be higher delays in detection by WAZE. So we looked at several of these factors, like weekday versus weekend, severity of the incidents, time of day, peak versus off peak, incident duration in Navigator, incident duration in WAZE, and so on and so forth. But we did not see any major difference in the shapes of the distribution in any of these cases. So we essentially did not observe an influence of these factors on significantly changing the proportion of the incidents where WAZE detected the incidents before Navigator. So this one is a comparison of the AM peak versus the PM peak versus the off peak. So as you see, as I click through this, once you'll notice very slight changes in the distribution. Well, this is the frequency, so the height is changing, but the shape essentially remains the same. So now we did, however, note a difference in the matching rate of the incidents based on some WAZE attributes. For example, the left-hand chart here at the bottom shows the frequency distribution of the raw WAZE incidents, and the one on the right here shows the frequency distribution of the matched incidents. So the WAZE reports with a higher report rating had a slightly higher match. So you see these are almost parallel here at the top, whereas this one is slightly higher than this. So it's slight, but there is a difference here. So the matched ones have a higher value here, higher report rating for the value for the report rating here, which indicates that a WAZE report with a higher report rating had a higher probability of matching with a navigator incident. So we looked at other factors like the confidence value reported in WAZE and the reliability value reported in WAZE, and we saw a similar change, a shift in the proportion in the matches. So essentially, that tells us that incidents with higher confidence or a higher reliability, as indicated in WAZE, would have a higher probability of finding a matched navigator incident. No surprises there, but it's nice to see a confirmation there. So that's all I had for this WAZE study. So this naturally flows into the second part of the study, where we see that while WAZE is a great complement, and there are conditions under which the crowdsourced detection might not really be sufficient. So there is still room for other detection technologies such as automatic incident detection technologies. Incident detection technologies are not new, and we are quite aware that automatic incident detection technology presents a great opportunity to enhance incident detection. But we know that most automated incident detection technologies do generate a high volume of alerts. It is usually beyond the resources of the incident management programs, and in most cases really honestly unnecessary to respond to all of them. It means that there are incidents that just clear by themselves. Means people pull over and start back again. So in this part of the study, we developed a methodology to sieve through the hundreds of the alerts and automatically identify the most critical alerts in real time. So the video-based incident detection, automatic incident detection system was deployed on a test bed on a 16-mile stretch of I-475 in Macon, Georgia. This small red line you see here, that's Macon. This is the screenshot of the AID web interface. So there were 186 cameras. It's a zoomed in view of Macon here. So these were deployed in clusters, right? If you have one pole, means you have 3 cameras on it pointing in different directions, covering different areas of the roadway. So we had like 43 groups of these cameras. Now, the incidents that are generated by the AID can be of various types. A stopped incident, a vehicle going in the wrong way, or a pedestrian coming out of the vehicle and walking on a freeway. These are all incidents that we know. Congested traffic and slow-moving traffic are not really incidents per se, but these could be monitored by traffic operations for congestion management. So in the I-475 deployment, we saw that the large majority of the incidents were stopped incidents. And this is in line with what we see for the Georgia Navigator logs on this chart on the bottom right, where the majority are tagged as stalls. So of interest here is that the stopped incidents in this pie chart on the here, and so these were 88% of these were on the shoulder. It's a if we look at the number of incidents on this 16-mile corridor, which is 32 miles of unidirectional roadway, there is an average of 100 alerts per day, more than 100. There are certain hours where you can get up to 7 to 8 alerts per hour. Now, this doesn't sound too many, but if you project that out to say 10 times that length, say 160 miles, that number jumps to 80 alerts per hour and suddenly becomes significant. Right? So the fact of the matter is that these are not, it's not like these alerts are false. Most of these alerts are true. There are definitely some instances where you have a shifting of the cameras generating some alarms, or if you have some branches of trees moving, generating alerts, or a shoulder being detected as an incident on the lane. These kind of cases were few and far between. The vast majority of these alerts were actually true. There was a vehicle stopped or somewhere within the view. So we looked at 10,000 of these alerts manually and verified them. And found that the vast majority was true. So the distinction we are trying to make here is whether these alerts are significant enough to require a response. So, so to develop the algorithm for filtering out the non-critical alerts, we started again at the navigator logs and the automatic incident detection logs. The AID system also keeps a log of the images and the video clips for the incidents, a short clip. So we manually reviewed all these 10,000 alerts and the images and the videos associated with them as available. Means not all of them had a video, but mostly all of them had at least an image. So we compared those with the navigator logs. We looked at the videos, and we manually identified a set of incidents that we believed were critical enough to require a response. So due to the sheer magnitude of the number of alerts, there were multiple incidents going on along the corridor at the same time. Right? In some of the cases, when it was in the wrong direction, so we could obviously eliminate those. But still, if you look at this, means we have 1, 2, 3, 4, 5, 6, 7, 8 in the same area, where it could have been, any of those could have been associated with this darker orange spot, which is the navigator incident. And so exactly tying the navigator incident to an alert in the AID was not quite that simple. So what we did was what we transportation engineers and researchers do. We threw everything into a time-space plot, right? So we have the distance on the y-axis, and these are not really, so 1, 2, 3, 4 is not really mile, but these are blocks of 3.4 miles. Sorry for that confusion. So this represents about 16 miles overall, right? And this is the northbound direction, and so all these spots are all the alerts versus these colored ones are the red, green, or yellow, orange ones, and these dark blue. These are the ones corresponding to the actual, the spots corresponding to the actual incidents here. So These look fairly non-informative in this plot, but if we zoom in this section, these will start to make sense. So we the previous plot was 60 days worth of data, right? When we zoomed in on this one particular case, we see the telltale slope that is characteristic of a backward moving shock wave or a brake light wave, right? We saw several occurrences of these. So when we zoomed into each of these, we saw let me zoom in further into this. So we saw the expected slope in some of these, right? And we see it in this one, we see it somewhat in this one and this. Well, so by the way, these yellow streaks here, those are the navigator incident. So this is the start of the navigator incident, and the end is outside of this chart here. But and these dots represent each dot represents an alert. The colors are different types of alerts. Anyway, so we see that these alerts started a little before it was actually logged in Navigator. Anyway, so in some of these we see this expected pattern, in others we don't. But what we do see are these clusters occurring, right? So, but the problem here is that we